In this video, I will be discussing about first-order linear differential equations. So our goal in this video is to develop a method of solving a differential equation which is linear in the dependent variable and of the first order in its derivative. Actually, a first-order differential equation is said to be linear if it can be written in the following form: dy dx plus y times a of x, which is equal to b of x. Now, this differential equation is a first-order differential equation because you can see here that this is the first derivative of y with respect to x. And this is linear in the dependent variable y. And also, these a and b are functions of x. So if you have a differential equation of this form, then this is a first-order linear differential equation. And the other form is dx dy plus x times a of y, which is equal to b of y. So this differential equation is also a first-order differential equation because this is the first derivative of x with respect to y. And this is linear in the dependent variable x here. And a and b are also functions of y. So here, our dependent variable is x, but our independent variable is y. Now, let us determine the solution of this standard form number 1. The derivative of y with respect to x plus y times a of x, which is equal to b of x. So, the solution to this type of equation is actually with the help of the integrating factor phi here. So, in obtaining the solution of the standard differential equation number 1 here, we need to multiply our integrating factor phi to both sides of the equation. So whenever we say phi here means a function of x. So it is phi of x. So phi of x times derivative of y with respect to x plus the phi of x times y times a of x, which is equal to the phi of x times the b of x. So as you can see here, we are multiplying each term in this equation by our integrating factor phi of x. Now, we notice that this left side part of the equation is somewhat like a derivative of a product. So here, we may assume that this is a derivative of a product, say phi of x times y. And of course, this is with respect to x because this involves phi of x and the dependent variable y. So if this is equal to this, we may write that the derivative of this product is equal to this phi of x here times the derivative of y with respect to x plus phi of x times y times a of x here. So substituting this one to our equation 1, so this is our equation 1. We have the derivative of phi of x times y, which is equal to this one here. So phi of x times the b of x. And multiplying both sides of the equation by dx, we have the differential of the phi of x times y, which is equal to the phi of x times b of x times dx here. because you are multiplying both sides of the equation by dx. And we notice that this phi of x and b of x are functions that are in terms of x alone. So if you integrate both sides of the equation, so the integral of the differential of the phi of x times y, which is equal to the integral of the phi of x times b of x dx here, then we notice that the integral of the differential cancels each other. So what will remain is the phi of x times y, which is equal to the integral of the phi of x times the b of x dx, plus the constant of integration c. So solving for our y, we need to divide both sides of the equation by this phi of x. So we have y, which is equal to 1 over the phi of x times the quantity of the integral of the phi of x times the b of x dx, plus the constant of integration c. So this is now our solution for this standard form of the first order linear differential equation. So the problem here is to find this phi function such that when multiplied to both sides of the equation, this is the solution. So now we need to solve for the phi of x from our assumption. From this one here. So if we write this one, the derivative with respect to x of our phi of x times y, which is equal to the phi of x dy dx plus the phi of x times y times a of x. And applying the rule for the derivative of a product, we have phi of x times the derivative of y with respect to x plus y times the derivative of phi of x, which is phi prime of x. And you can check that this one is this here, and we get the derivative of this plus y times the derivative of this. And this is equal to the phi of x times the derivative of y with respect to x plus the phi of x times y times the a of x here. And we notice that we have similar terms from both sides of the equation, this one and this one here. And also this term with this term have a common factor, which is y. So you can divide both sides of the equation by y. So what remains is the phi prime of x, which is equal to phi of x times a of x. And to solve for the phi of x, because that is our goal, we need a trick here. And the trick is to divide both sides of the equation by the phi of x. So this phi prime of x divided by phi of x, which is equal to a of x here, because the phi of x at the right will be cancelled when divided by p of x. And taking the integral to both sides of this equation with respect to x, here we have this as the natural log of the phi of x, because the integral of the derivative of this function divided by the function itself is just the natural log of this function. And this is equal to the integral of a of x dx here. And raising both sides of the equation to e, we have this natural log here will be cancelled. So this is phi of x, which is equal to e raised to the integral of a of x dx. So this is now our integrating factor that we need for our solution here. And also, to solve for the solution of this standard form number 2, which is linear in the dependent variable x, we need to multiply this integrating factor phi to both sides of the equation. So we have this phi of y times dx dy here plus phi of y times x times a of y, which is equal to the phi of y times b of y. And again, we notice that this is somewhat like a derivative of a product. So let us make our assumption here that this is a derivative of a product of phi of y and x here, because it involves phi of y and the dependent variable x. So this is equal to phi of y times dx dy plus the phi of y times x times a of y. So substituting this assumption to this equation number 2, because this is our equation 2, we have the derivative with respect to y of this phi of y times x, because we assume that this one is equal to this. So instead of writing this one, we will write this one here. So this is equal to the phi of y times the b of y, and multiplying both sides of the equation by dy, we have the differential of the phi of y times x is equal to the phi of y times b of y dy. And integrating both sides of the equation, we have the integral of the differential of the phi of y times x, which is equal to the integral of the phi of y times the b of y dy here. And we noticed that the integral and the differential cancels each other. So what remains is the phi of y times x, which is equal to the integral of the phi of y times the b of y dy plus the constant of integration c, because we have done our integration here. So solving for our x, we need to divide both sides of the equation by the phi of y. So our x is equal to 1 over the phi of y times the quantity of the integral of the phi of y times the b of y dy plus the constant of integration c here. And this is our solution for this first order linear differential equation. But the problem here is, how do we find our integrating factor phi of y? So solving this integrating factor phi of y, we can solve this one from our assumption that we have, that our assumption is that this one is equal to this. So we need to find the derivative of this product with respect to y. And the derivative is phi of y times the derivative of x with respect to y here, plus x times the derivative of our phi of y which is phi prime of y, which is equal to this one here. So we write here, this is equal to the phi of y times the derivative of x with respect to y plus the phi of y times x times the a of y. And we notice that this term at the left side of the equation is equal to this term at the right. So we may cancel this one here and say that this term is equal to this term. But we notice that the two terms have common factor of x, so we may divide both sides of the equation by x, so that what remains at the left is the phi prime of y, which is equal to the right hand side, which is phi of y times a of y. And the goal is to solve for the phi of y. Now, solving for our phi of y here, we need the trick by dividing both sides of the equation by the phi of y. So we have phi prime of y divided by phi of y, and at the right, the phi of y will be cancelled. So this is a of y alone. And taking the integral both sides of the equation with respect to y, here we have this as the natural log of the phi of y, because we know from your integral calculus that the integral of the derivative of a function divided by the function itself is equal to the natural log of that function. And this is equal to the integral of a of y dy here. And erasing both sides of the equation by e, we have this natural log cancelled with the e. So what remains is the phi of y, which is equal to e to the power of the integral of the a of y dy here. And this is our integrating factor, phi of y, that we need for our solution for this standard form number 2, which is linear in the dependent variable x, and it is first order in the derivative of x with respect to y. And applying this one to an example, we have example 1 here. Find the general solution to the differential equation dy dx plus 2xy, which is equal to 6x. And we notice that this is already a standard form, because if we write this one as the derivative of y with respect to x plus 2x times y, which is equal to 6x, we have that this differential equation is a first order differential equation in the derivative of y with respect to x. So therefore, this differential equation is linear in the dependent variable y here, and it is a first order derivative of y with respect to x. So we say that this is our a of x here, and this one is our b of x, because as you can remember that our standard form number 1 is the derivative of y with respect to x plus a of x times y, which is equal to the b of x. Therefore, in this standard form, we have the derivative of y with respect to x added to some function of x times the dependent variable y, which is equal to another function of x without a y. So we say that this is our a of x, and this 6x without a y is our b of x. So we can find this time our integrating factor, which is the phi of x, which is equal to e raised to the exponent of the integral of a of x dx here. And our a of x is 2x. So this is equal to e to the power of 2 if you factor out 2 in front of the integral. So this is 2 times the integral of x dx. And we have that our phi of x is equal to e to the power of 2 times x squared over 2 here. And simplifying, we have e to the power x squared. So our phi function is this one here. So this is our integrating factor that we need to our solution function. Then our solution function y, which is of the form 1 over phi of x times the integral of phi of x times the b of x dx plus the constant of integration c. And substituting our integrating factor phi of x, we have 1 over e to the power x squared times the integral of e to the power x squared times the b of x, which is 6x dx, plus the constant of integration c. And we know that the derivative of x squared is only 2x. So we have an extra factor of 3 here. So we need to factor out the 3 outside the integral symbol. We have 1 over e to the power x squared times the integral of e to the power x squared times 2x dx here, but the 3 will be factored in front of the integral because 3 times 2 is 6, and this is added to the constant of integration c. So we have our solution function, which is equal to 1 over e to the power x squared times 3 times the integral of e to the power x squared times 2x dx is e to the power x squared. And this is added to the constant of integration c. So y is equal to 3 because if you distribute this one here, this e to the power x squared and this e to the power x squared will be cancelled. So what remains is 1 times 3, which is 3, plus this 1 times this c here. So this is c over e to the power x squared. Or you may simplify it further as y, which is equal to 3 plus the constant of integration c times e to the power negative x squared. So this is our solution for this given differential equation, which is a first order linear differential equation, which is a linear in the dependent variable y here. Now let's proceed to our example number 2. Find the particular solution to this differential equation to y plus 4x to the power of 4 dx minus x dy, which is equal to 0, where y of 1 is equal to 4. So this is an initial value problem because we have here an initial condition. So to solve this problem, we need to distribute this dx to these two terms here. So we have 2y dx plus 4x to the power of 4 dx minus x dy, which is equal to 0. And you notice that we have two terms that are in terms of dx, whereas there is only one term that is in terms of dy. Since we have only one dy, we understand that y is our dependent variable. So if this is our dependent variable, we need to eliminate this dx in these two terms by multiplying both sides of the equation by 1 over dx, so that the dx in these two terms will be cancelled, and I will add a negative here so that this term will become positive. So this 1 over dx times this term, we have a negative 2y, because this dx and this dx cancels each other. And also this dx with this dx here cancels each other. So this is negative 4x to the power of 4 because of the negative 1 there, plus x times dy dx here, which is equal to 0. And we notice that our dy dx still contains a coefficient of x. So we need to eliminate this x here so that this differential equation can be a standard form of a first order linear differential equation. And we can do that by multiplying this resulting equation by 1 over x. So multiplying both sides of the equation by 1 over x. So the result is negative 2y over x minus 4x cubed, because this is x to the power 4 divided by x. The result is x cubed, plus derivative of y with respect to x, because this x here and this x in the denominator cancels each other, and this is equal to 0. So rewriting this resulting equation so that it will fit to a standard form of a first order linear differential equation, we write this dy dx as our first term, and then minus 2y over x, which is equal to 4x cubed, because this is linear in y. And rewriting this one further as dy dx, we have 2 over x times y, which is equal to 4x cubed. Now, remember that our standard form is having a form of dy dx plus a of x times y, which is equal to b of x. So that is why I write this 4x cubed at the right, because that is the only term that is in terms of x without a factor of y. And we write also this term as 2 over x times y. So we understand that our a of x there is negative 2 over x. So we include the negative here because the standard is always positive. And our b of x here is equal to 4x cubed. So this is linear in y because of this y here. And this is the first order in the derivative of y with respect to x. So we can now find our integrating factor phi of x. And we know that phi of x has a formula of e raised to the power of the integral of a of x dx here. So since our a of x is negative 2 over x there, we have to factor out the negative 2 outside the integral symbol. So this is negative 2 times the integral of dx over x. And we know that the integral of dx over x is ln x. So this is e to the power negative 2 times ln x. And applying the property of logarithms, we have e to the power ln x to the power negative 2, because this negative 2 can be an exponent to x. And further, by the property of logarithms and exponentials, this e here and this ln here cancels each other. So this is x to the power negative 2. And this is our integrating factor here. So then our solution function is equal to y, which is 1 over the phi of x, and the phi of x is x to the power negative 2 times the integral of our phi of x, which is x to the power negative 2 times b of x, which is 4x cubed, and then dx plus the constant of integration c. So we have y, which is equal to x squared times the integral of 4x dx plus the constant of integration c, because applying the laws of the exponent, this 3 and the negative 2, when added, that is equal to 1. So factoring out our constant of 4 outside the integral symbol, we have 4 times the integral of x dx plus the constant of integration c. So we have y, which is equal to x squared times 4 times the integral of x, which is x squared over 2 plus the constant of integration c there. And therefore we have y, which is equal to x squared times 2x squared, because 4 divided by 2 is 2. And this is added to the constant of integration c. So we have y, which is equal to 2x to the 4th. When you distribute this one here, and also this x squared to this c, we have plus c x squared. And also it is given that the y of 1 is 4, which means that when x is 1, the y is 4. So substituting these values here to our solution, we can obtain our c. So y equals 2x to the 4th plus cx squared. We have y is 4 when your x is 1. So this is the resulting equation. So simplifying it further, we have 2 times 1, which is 2, and c times 1, which is c. Therefore 4 minus 2 is equal to c. So c is equal to 2. Now that we have our value of the constant of integration, we can find our particular solution, which is y, which is equal to 2x to the 4th plus 2x squared. And this is our particular solution for the given differential equation. Now let's proceed to our example number 3. Determine the general solution to this differential equation. So to solve this one, we need to distribute this dy to this trinomial here. So we have y dx, which is equal to e to the power y dy plus 2xy dy minus 2x dy. And since we have 3 terms here that contains dy versus 1 term that contains dx, we can now determine that our dependent variable is x, because we have only 1 dx here. So we need to eliminate these dy's in these 3 terms here by multiplying each term in the equation by 1 over dy. So we have y dx dy, which is equal to e to the power y, because this dy cancels with this, plus 2xy minus 2x here, because all of these dy's will be cancelled with this dy here. But we notice that our derivative of x with respect to y has a coefficient of y. So we need also to eliminate y by multiplying both sides of the equation by 1 over y. So we have dx over dy, which is equal to e to the power y over y plus 2x minus 2x over y. And to convert this one to a first order linear differential equation, because this is first order in the derivative of x with respect to y, we suspect that this is linear in x. And since this is a first order derivative of x with respect to y, then we can transform this one into a first order linear differential equation which is linear in x, wherein y is our independent variable. So to convert this one to its standard form, which is standard form number 2 in our discussion here, we need to move all the terms that is in terms of y but with an x coefficient. So we have dx dy plus 2x over y, because this has a coefficient of x, minus 2x here, which is equal to e to the power y over y, because this is the only term that is in terms of y alone. So factoring our x in these two terms, we have dx over dy plus 2 over y minus 2 times x, which is equal to e to the power y over y here. And we understand that this is our a of y, and this is also our b of y in our standard form number 2, because as you can recall, our standard form is derivative of x with respect to y, which is added to a of y times x, which is equal to b of y. So here, our a of y is this one, and our b of y is this term. So we can now find our integrating factor phi of y. So phi of y, according to our formula, this is e raised to the exponent of the integral of a of y dy. And since we know our a of y, we have e to the power of the integral of a of y, which is 2 over y minus 2 dy. We have this e to the power of the integral of 2 dy over y minus the integral of 2 dy here. And factoring these constants outside the integral symbol, we have our phi of y, which is equal to e raised to the exponent of 2 times the integral of dy over y minus 2 times the integral of dy. So our phi of y here is equal to e raised to the exponent of ln y, because we know that the integral of dy over y is ln y minus 2y here. So therefore, applying the properties of logarithms, these two can be the exponent of y. So this is ln of y squared, and then subtracted by 2y. So applying the laws of the exponents, we have e to the power ln of y squared times e to the power negative 2y. And simplifying it further, we have y squared, because this e and this ln cancels each other by the properties of logarithms and exponentials. And this is multiplied by e to the power negative 2y. And now that we have our integrating factor, we can determine our solution function, which is x, that it is 1 over our phi of y times the quantity of the integral of the phi of y times the b of y dy plus the constant of integration c. So substituting this phi of y, which is y squared times e to the power negative 2y times the integral of our phi of y, which is y squared times e to the power negative 2y times our b of y, which is this one here, e to the power y over y dy plus the constant of integration c. And this is equal to e to the power 2y over y squared, because we move this factor to the numerator to make the exponent positive. And this is multiplied to the integral of y times e to the power negative y dy plus the constant of integration c, because one of the y in this y squared will be cancelled to this y in the denominator, and adding this exponent here, y and negative 2y, we have negative y. So looking at this integrand here, we notice that this is a product of an algebraic function and an exponential function. Therefore, to integrate this one, we can apply our integration by parts, wherein this y is our u and the remaining part is our dv here. So letting u as y and our dv as e to the negative y dy, we can solve for our du, which is equal to dy. And solving for our v from this equation, we need to integrate both sides of the equation. So we have the integral of e to the power negative y dy here, and v is equal to the integral of e to the power negative y times negative dy, because the differential of negative y is negative dy. But to neutralize this added negative sign here, I need to have a negative in front of the integral symbol. So we have our v, which is equal to the negative of e to the power negative y. So substituting our u and v to our integrand, we have x, which is equal to e to the power 2y over y squared times the integral of u dv. Because instead of writing y, I will write u, and instead of writing e to the power negative y dy, I will write dv, because that is our representation here. So using our formula for integration by parts, we have the integral of u dv as uv minus the integral of v du, and this is added to the constant of integration c. So we have our x, which is e to the power 2y over y squared times our u, which is y, and our v, which is negative e to the power negative y minus the integral of negative e to the negative y times du, which is dy here. And this is added to our constant of integration c. Now, you can integrate this time our integrand, because we have here this negative y e to the power negative y minus the integral of e to the power negative y negative dy here, plus the constant of integration c. So this is equal to e to the power 2y over y squared times the quantity of negative y e to the negative y minus e to the negative y, because the integral of this one is e to the negative y plus the constant of integration c. And multiplying this fraction to each term of this trinomial, we have x, which is equal to e to the power 2y times e to the power negative y. We have negative y e to the power y over y squared, and this will be subtracted by e to the power y, and also plus c times e to the power 2y. And multiplying both sides of the equation by y squared, this y squared will be cancelled by this one, but this y squared will be multiplied to x. So we have x y squared plus y e to the power y plus e to the power y, which is equal to c e to the power 2y. And you notice that these two terms are positive because we are moving these two terms to the left side of the equation. And this is our answer to this example number 3. Now let's proceed to our example number 4. Find the general solution to this differential equation. Now, to solve for this differential equation, we need to determine which variable is our dependent variable. And as you can notice, we have only one dy, but we have 3 dx here. So therefore, our dependent variable is y because we have only one dy. So to eliminate this dx here, we need to multiply both sides of the equation by 1 over dx. So we have dy minus y tangent x dx, which is equal to dx minus the quantity of x plus 5 times tangent x dx. And removing our 3 dx by multiplying 1 over dx, we have dy dx, which is subtracted by y tangent x, which is equal to 1 minus the quantity of x plus 5 times tangent x here. And we notice that this is already in a standard form for the first order linear differential equation, because this is the first order of the derivative of y with respect to x. So therefore our y is the dependent variable and our x is our independent variable. So this is linear in y. So therefore all the terms without y will be moved at the right. And since we have already all the terms at the right which are in terms of x alone, we understand that our a of x is negative tangent x, because we can write this negative as the sign of tangent x, and this is equated to the whole function in terms of x, which is 1 times x plus 5 times tangent x. So we understand that this is our a of x and this is our b of x, because as you can recall, that our standard form number 1 is having a form of derivative of y with respect to x plus a of x times y, which is equal to the b of x. So therefore, our a of x here is equal to the negative tangent x, and our b of x is equal to 1 minus the quantity of x plus 5 times tangent x. And since we know already our a of x, then we can find our integrating factor phi of x, which is equal to e to the power of the integral of a of x dx. And our a of x is negative tangent x dx. And this negative tangent x can be expressed as the negative sine x over cosine x dx. And we know that if you let the cosine x as your u, the derivative is negative sine x there. So if you let u be cosine x, we realize that our du is negative sine x dx. So by substitution, we have e to the power of the integral of du over u here. And we know that the integral of du over u is ln u. And applying the properties of logarithms and exponentials, this exponential and logarithm cancels each other. So this is equal to u, but our u is just cosine x. So therefore, our phi of x is just cosine x. And that is our integrating factor. Then therefore, our solution function, which is 1 over the phi of x times the quantity of the integral of phi of x times the b of x dx plus the constant of integration c there. So we have y, which is equal to 1 over cosine x times the integral of cosine x times the b of x, which is 1 minus the quantity of x plus 5 times the tangent x dx plus the constant of integration c there. So simplifying it further, we have 1 over cosine x times the integral of cosine x. If you distribute this one to the first term here, and also cosine x to this one, which is x plus 5 times cosine x times the tangent, which is sine x over cosine x. And this is with respect to x. And this is added to the constant of integration c. So therefore, our solution function y, which is 1 over cosine x times the quantity of the integral of cosine x minus x plus 5 times sine x, because this cosine x here and this cosine x will be cancelled here. And this is added to the constant of integration c. But with a certain creativity, we recognize that this is already a differential of a product. So rewriting our solution function y, which is 1 over cosine x times the integral of the differential of cosine x times x plus 5, because we realize that if we get the derivative of this product, we have cosine x, which is this one, times the derivative of x plus 5, which is 1. And then plus this x plus 5 here times the derivative of cosine x, which is negative sine x. So therefore, this is exactly a differential of a product. So integrating a differential will cancel each other. So our y, which is equal to 1 over cosine x times the quantity of the cosine x times x plus 5. And this is added to the constant of integration c. So distributing our fraction 1 over cosine, we have y, which is equal to x plus 5 plus c over cosine x. But this cosine x in the denominator can be rewritten as second x. So this is c times the second x. And this is our solution for the given differential equation. Now let's proceed to our last example here. Determine the general solution for this differential equation. And to determine which one is our dependent variable here, we need to distribute our dv in this trinomial here. So we have v dx plus 2x dv plus 1 dv minus vx dv, which is equal to 0. Now as you can see that there are two variables there, the v and the x. So our goal is to determine now which one is our dependent variable. And since we have three terms that have dv's as their coefficients, we understand that our dependent variable is x this time. So we need to eliminate this dv for these three terms by multiplying both sides of the equation by 1 over dv. So we have v dx dv plus 2x plus 1 minus vx, which is equal to 0. But since we have a v as a coefficient of this dx over dv, we need to eliminate that v by multiplying 1 over v to both sides of the equation. So we have dx over dv plus 2x over v plus 1 over v minus x is equal to 0 here. And since this is a first order derivative of x with respect to v, then our dependent variable is x and v is our independent variable. So this is first order linear differential equation, which is linear in x. So we need to have terms that have coefficients of x aside from dx dv here at the left side of the equation. So we move this 1 over v to the right hand side of the equation because this is the only term that has no x. So we have dx dv plus 2x over v minus x, which is equal to the negative 1 over v. And factoring the x in these two terms, we have dx dv, and this is added to 2 over v minus 1 times x, which is equal to negative 1 over v. So this is our a of v here, and this is our b of v here, because our standard form for this differential equation, we have dx dv plus a of v times x, because this is linear in x, and this is equal to b of v because our independent variable is v. Then therefore, we can find our integrating factor phi of v here, which is equal to e to the power of the integral of a of v dv here. And since our a of v is 2 over v minus 1 dv here, we have e to the power of the integral of 2 over v dv minus the integral of dv. So factoring these two outside the integral symbol, we have 2 times the integral of dv over v, and this is subtracted by the integral of dv. So we have our phi of v, which is equal to e to the power of 2 times ln v, and the integral of dv is v. So applying the laws of exponents, we have e to the power 2 ln v times e to the power negative v. But using the properties of logarithms, these two can be the exponent of v. So we have e to the power ln v squared, and this is multiplied by e to the power negative v. And by the properties of logarithms and exponentials, this e and this natural log cancels each other. So this is v squared times e to the power negative v. And this is now our integrating factor phi. Now, we can find our solution function for the differential equation. So x is equal to 1 over phi of v times the quantity of the integral of the phi of v times the b of v dv here. And this is added to the constant of integration c. So substituting our phi, we have 1 over v squared times e to the negative v times the quantity of the integral of v squared times e to the negative v times the b, which is 1 over v but negative dv here, plus the constant of integration c. So we have x, which is equal to e to the power of v over v squared, because we are moving this e to the negative v here in the numerator. Then we multiply this one by the integral of v, because one of the v in this v squared will be cancelled by this v, and this is multiplied by e to the power negative v dv here. But this negative can be placed outside the integral symbol there. So looking at this integrand, we notice that this is a product of the algebraic and the exponential part. So we apply here integration by parts, that this is our u here. So when you let u be v and the remaining part is our dw, so dw is equal to e to the power negative v dv here. I'm using dw because we have already dv here. So finding the du is dv here, and finding the w, we need to integrate both sides of the equation. So we have the integral of negative v dv here, and we know that the differential of negative v is negative dv. So we have the integral of e to the power negative v times negative dv. And to neutralize this added negative here, we need to add a negative outside the integral symbol. So we have our w, which is equal to the negative of e to the power negative v. substituting our u and our dw to our original integrand, we have x, which is equal to e to the power v over v squared times the negative of the integral of u dw plus the constant of integration c. So therefore x is equal to e to the power v over v squared, and we know that this is equal to the uw minus the integral of w du here plus the constant of integration c. So x is equal to e to the power v over v squared times the negative of the quantity of u, which is v, and our w, which is negative e to the negative v, plus, because the negative of the negative is positive, the integral of w, which is negative e to the negative v times du, which is dv here. And this is added to the constant of integration c. So x is equal to e to the power v over v squared times the quantity of v e to the power negative v, because the negative of the negative is positive, and this is added to the integral of e to the power negative v times negative dv is e to the negative v plus the constant of integration c. Distributing our e to the power v to these three terms here, we have v plus 1 plus c e to the power of v all over v squared. So multiplying both sides of the equation by v squared, we have x v squared, which is equal to v plus 1 plus c e to the power of v here. And this is our solution for the given differential equation. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.